Alright, so this free response is kind of mathematically heavy but fairly straightforward. It's really good practice for doing a useful free body diagram and carefully talking about vector components and then applying Newton's laws, which is hopefully what you got out of it. So, first step is to draw a free body diagram on our block that's on an incline and it's sliding up the inclined plane. And the reason that matters it slides up is that's going to tell us the direction of friction. So there's a weight and a normal force, kind of like always. There's the force capital F, the applied force, or the whatever the hand pushing or something it might be. And then there is kinetic friction, right? And additionally, I'm going to draw this on now, right? I'm going to draw the coordinate system that we want to be using, right? The tilted coordinate system. And there's a couple angles that we know, right? This is theta, and that is theta. So what's drawn in red should be all that you draw on the figure for figure A. If you want to do anything more than that, you should draw another figure to the side rather than edit the one, so that way it's easy to grade for the AP people. All right. So we've got our forces. The next part is to solve for acceleration, basically, right? And we know that that is in the horizontal or the up to plane direction. So we're going to have to write the net force, I'm going to call it the x direction, equals ma. And now let's look at those forces that we have. We have friction down the plane. That one's easy. Then we have to do some component work, right? Our weight force has part of the weight that's down the plane as well, right? So we have a minus mg for weight, and that's the opposite side, so sine theta. And then we also have part of the force capital F. And this time it's cosine, right? It's the adjacent side that points up the incline, so plus, and that equals ma. Alright, so this is looking promising. Theta is okay to use, m is okay to use, g is okay to use, but the force of friction is not, right? That's not a given quantity. All we know is the coefficient of friction. And since we know this is then mu times n for the force of friction, now we need to figure out the normal force. And here's where you can make a mistake if you're not being careful. The normal force is determined by the vertical equilibrium statement, right? That in the vertical direction the net force is 0. It's not the weight, always. It's not a component of the weight, always, because in this case we have a lot of forces in the vertical direction. You always have to set up the equation and solve. So if we want to figure out the normal force, we have to go sort of do a side step to figure out Newton's laws in the vertical direction. So the normal force, positive, minus part of the weight, right, that's that component, and also minus part of the force F, right? That's what Newton's laws in the vertical direction tells us. You don't assume anything about the normal force, you have to solve for it. And if we do some algebra, we can solve for the normal force. Right? And that's good. Now we can plug that in. So erase the normal force and put that whole thing in parentheses. Right? And now we've essentially solved it. All we have to do is divide both sides by m, right? So, divide by m, and clean up the other side, right? Rather than rewrite that whole mess. And that's the answer, right? You can algebraically simplify that if you want, right? Some of the masses will cancel. You could distribute the mu, but, that doesn't really matter. This answers the question. A in terms of the things that we're given. Right, so that's part B. A lot of algebra and a lot of doing the steps rather than making any assumptions. For part C, now we're trying to solve for f when a equals to 0. So we're going to take that big and ugly expression that we had, and we're just going to say a equals 0. So I have to rewrite that, which is negative mu. Actually, I'm going to do some distribution as I write it, just for simplicity, to save some of the algebra time. So let's actually look at that. So 0 equals f over m cosine theta minus g sine theta minus mu g cosine theta plus mu f over m sine theta, right? So if we want to solve for f, we need to put all those terms on one side and move everything else to the other side. So that's g sine theta plus mu g cosine theta equals f, and we factor out the other stuff. Right? And we notice we can multiply both sides by m, right? We're sort of undoing a step here actually, but that's okay. So we have mg sine theta and mu mg cosine theta. And then we have to divide by cos theta plus mu sine theta. And this equals f. Right, so that's the first part, right? It's just algebra. But the second part, once you get to this point, now, oops, hang on, I've got a sign error. Yeah, I've got a sign error in here, so I have to make some slight changes. As I was copying this over, this is a minus, not a plus. And so I'm just going to make that change. So as you get to this point, now you have to look at the second part. What relation must theta and mu satisfy in order for the solution to be physically meaningful? So there's a couple different pieces to this, but physically meaningful means that the value for force F that we calculate has to match what's happening in the problem. So force F points to the right in the positive direction. If we calculate something for F and get a negative number, that would mean force F would point to the left, which it can't, right? If force F points to the left, the block does not go up the incline. So our rules for it to be physically meaningful are really, right, I'm not sure if actually I'm going to be able to write that very usefully. Really what this means, when I say physically meaningful, is that F has to be greater than 0. If it's anything else, it doesn't make any logical sense. It wouldn't correctly describe the motion. So we have to then look at when could F be less than 0, and how do we make it that not happen? And that's going to be in the denominator, right? The numerator is always positive, so that's easy, right? For angles of theta between 0 and 90 degrees, which that incline has. But if cosine theta is less than mu sine theta, then F would be negative, right? So our requirement, the requirement must be that the opposite is then true, right? That cosine theta is greater than mu sine theta, right? This is the requirement that makes it physically meaningful. And so all we need to do is kind of rearrange that a little bit. And so I'm just going to go to one more slide. So if we have cosine theta greater than mu sine theta, then we can rearrange to get mu must be less than cotangent theta, right? And so that's your condition on a relationship between mu and theta such that the solution is physically meaningful.